Okay, SWR, we talked about it. Let's say what it is. Okay, it's called the standing wave ratio. So when you are sending a signal over the feed line, whether it's coax or twin lead, if you have a mismatch at the antenna, you'll get part of that signal reflected back. And depending on the phasing of it, it can either add or subtract from the forward signal. So you can get a much higher voltage, which is why they call it standing wave ratio. So you can have very, very high peaks, 2 to 3 times perhaps of what you would normally have on your signal. And they use that ratio, okay, as a measure of how good you're matched. So a perfectly matched system would mean you got a 50 ohm transmitter, you got a 50 ohm transmission line, and you got what appears to be a 50 ohm antenna. You're going to have a 1-to-1 SWR match.
Is that frequency dependent though? So if I pick...
It is on the antenna, it won't be on your transceiver, or it won't be on the coax. Okay. And
well, the
I
reason
say that because coax has a characteristic impedance. In this case, we're talking 50 ohms. When it's matched, okay, when you're not feeding a 50 ohm coax into a 50 ohm load, its characteristic impedance can change a little bit because it's all based on the fact that it's based on a matched impedance. And it gets really complicated.
I was just curious.
It's modeled with a whole bunch of inductors and capacitors along there. They're frequency dependent.
Because I put an SWR meter on when I put a CB in my truck.
Right.
I get 1-to-1 on the low end. It's the higher I go, the more the more SWR, the ratio.
And that's
grows.
normal.
Okay. Oh, okay.
Your antenna is going to be resonant at one frequency. Okay. And any frequency above or below that is you're going to have some reactive components, which means the impedance is no longer looking like 50 ohms or whatever it was. It's going to change, and that's frequency dependent. Okay. So that's why your SWR changes, which is why you want to tune your antenna for the part of the band that you want to operate in.
Right. So
you can get the lowest SWR and the least amount of reflection coming back. Even though you may have, it may be showing 1-to-1, probably not really 1-to-1, and if that's it, it's at one frequency or a very small range.
Right. Yeah.
You can normally go up to about 1.5-to-1, which I think is about 4 or 5% reflection. Most transceivers, if they have a built-in antenna tuner, can match up to 3-to-1 without having an external. And I'm not sure where the antenna tuner came on. We still call them antenna tuners. It's a matching network. It doesn't tune anything. So if you've got an antenna system that's greater than 3-to-1, you really need an external matching unit, tuner. And most of the modern transceivers will actually start throttling power back when they see reflections coming back high enough to be a SWR 3 in some cases. They may even start before. I think mine 7300 may start decreasing power above 2. And that's really to protect the output transistors and the power amplifier. So what is a standing wave ratio?
A.
Yep. It's just a measure of how well the load is matched to the transmission. What reading on an SWR meter indicates a perfect impedance match between antenna and feed line?
I pick 1 to 1.
1 to 1.
We used to have the SWR problems on the tractor trailers when we had them too, when we switched over to the fiberglass body tractor trailers, because we could never get a good ground to the mount. We'd have to run another ground line to the mount to the frame of the truck.
Yeah, well, that would definitely change the impedance of the antenna. So going from fiberglass to metal, everything affects everything on an antenna. So anything that you change around it, particularly if you're going from metal, if it's closer, or changing it to non-metal, it will have an effect. And that change in impedance will change your SWR. So what does an SWR reading of 4 to 1 indicate?
Bad mismatch.
Yep. It means your transceiver is going to be shutting down.
If it doesn't burn up first.
No, it won't. They're pretty, well, I don't know about the Chinese ones.
Okay.
The Japanese made ones are pretty good. Okay. The SWR. Oh. Is Roger up there waiting before?
Maybe. I just noticed it.
Here it comes. Roger, are you back?
Hearing light.
Are you back with us, Roger?
Both of them have been cutting in and out.
Yeah, I'm keeping my video off because the internet in the hotel's not that great, so I want to keep the bandwidth kind of low here.
Okay.
That's okay. You have a radio face.
Ha! Thanks there, neighbor.
Well, I guess Roger's there. I don't know if he can hear us. Okay. So your SWR is going to be low when you have a good impedance match. It does not necessarily mean it's going to be 1 to 1, but when you're at a resonant point on the antenna, you're going to have your lowest SWR. Now, just because your antenna is resonant doesn't mean that it looks like 50 ohms. If you've got a half-wave dipole, half-wave off the ground, and it's horizontal, it's going to be up in the 70 ohm range. So even at resonance, it's not going to be a 1 to 1 match. But it'll be close enough. You'll be less than 1.5. And you can use the antenna tuner to try to get it a little bit lower, but you won't lose that much power. So if you're seeing a very high SWR, it means that you've got a bad impedance match somewhere along the line. It could be in a connector, it could be between the antenna and your feed line. And your losses are going to be high when you've got a very high SWR, because you're getting more power reflected back, which is reflected again, which may be reflected back again, until all of it gets dissipated into heat in the transmission line. So the bottom line is you're going to get less power to the antenna, and therefore less radiated power when you have a higher SWR than it's possible to get with your system. This little diagram kind of shows the effect of a reflected wave, and this was kind of done based on a sound wave, but it's the same principle. When you see this impedance mismatch, in this case a wall, or in fact, if this was light, this would be a reflecting surface. It's going to be part of it reflected back. And depending on the phasing, it can add or subtract to the original wave, which gives you the standing wave. And how high that standing wave is in relation to the forward wave is kind of how they calculate the standing wave ratio. It's actually a little more complicated formula, which you don't have to know beyond the expert. But what is the benefit of a low SWR?
Bravo.
Yeah, I like the antenna wear though. That's pretty good.
Yeah, antennas wear from the weather. I don't think they care about the electrons. What happens to power lost in a transmission line?
Charlie.
Yeah.
Yep. Power creates heat or radiation, one or the other. Okay, modern amateur radio transceivers reduce the output power if the SWR is higher than a particular point. Like I said, I think my ICOM 7300 starts doing it around an SWR of 2. They say that the internal tuner is able to match up to 3 to 1. I've never gone that far, so I haven't seen what happens if I try to put more than 3 to 1 in it, but then I have an external tuner in series, so it would kick in, and then there'd be a lot of clicking and clacking and stuff going on. So why do most modern solid-state transceivers reduce output power as SWR increases above a certain level?
A.
Right. Strictly to protect the output transistors and the power amplifier. Okay. When you go to get an SWR meter, and a lot of radios will have it built in, particularly if they have a built-in tuner, where they will show you what they're seeing as the SWR. But if you get an external one, you need to make sure that it operates over the frequency range you want to use. Most of them will operate in the HF range. There's a few that will do both HF and VHF, UHF. And you normally have to switch it from one to the other and have two sets of inputs and outputs. So if you had, I've got a 5100, which is a 2 meter, 70 centimeter, and a 7300, which is HF, and 6 meters, which is part of VHF. I could use that same SWR meter for both. I just have to flip the switch as to which one I'm using. You also need to make sure that it'll handle the power level. If you've got a normal transceiver at 100 watts, it isn't really much of an issue. Although there's some that are made specifically for QRP radios and will only handle 10 or 20 watts. So you at least need to make sure that it's good for 100 or 200 watts if you've got a normal base station. If you've got a power amplifier, maybe 1500 watts, then you need to make sure it'll do 1500 watts. So that's a whole nother set of SWR meters. And the price goes up exponentially. So if you're trying to use one outside the frequency range or the power range, you're going to get erroneous readings, and you more than likely will damage the meter, and it won't read at all. Now, some of them will actually display not only an SWR ratio, but forward power and reflected power. They actually have a directional watt meter built into it, so it senses power going both ways. You can display those. Which of the following should be considered when selecting an accessory SWR meter?
D.
Did you say delta?
Well, actually, it would probably be A, right? It wouldn't matter the types of modulation.
Modulation doesn't affect it or where it's located. You can actually put it, you could put it any place in the line, and you could have it at the antenna. You could have it somewhere in between, or you can normally you would have it close to your transceiver. Okay, so you can also measure it with a directional watt meter. And they make specialized ones like Bird, which is sort of the gold standard for watt meters. And it has a switch, and you measure forward or reverse. And they also have little calibrated plugins that you get for them for the power level and the frequency range. So depending on what power, what frequency, you have a different plug-in, and then you can measure forward and reverse, and you have to calculate what the SWR would be from that. In most cases, I think it's more important to know how much reflected power you got coming back than what the actual SWR number is. If you measure those, this below is the formula for calculating the SWR from the reflected and forward power. And they say you should normally install it between the transmitter and the antenna. Because that way you're seeing any effects due to the transmission line itself and the connectors, which all of the above could be giving you or could be adding to the SWR besides the antenna. So what instrument can you use to determine SWR out of the selection?
Delta.
Yeah.
Lambic pentameter. Isn't that, music
Poetry.
poetry? That's what it was, yeah.
And there's also iambic keyers.
Yeah, alpha.
Where's Alpha? Okay. Okay, antenna analyzers. Most of them will measure SWR. Some of them will also measure things like capacitive reactance, inductive reactance. They give you a Smith chart showing resistance, reactances, impedances. And like they're pointing out here that the SWR of an antenna system will be lowest at the resonant frequency. Okay, that doesn't mean that it's going to be 1-to-1. Because if your antenna is 75 ohms and you're feeding with a 50 ohm coax, even if the antenna is resonant, it's not going to be 1-to-1. It's going to be more like 1.5. And they're pointing out here that if you have some of the antenna analyzers, you can use them for doing other things besides just sweeping an antenna for SWR. You can measure your coax loss with a network analyzer type, we can show in a minute, and see how much loss you have from one end to the other of the coax at different frequencies. You can use it in TDR mode, which a lot of them will do, which is time domain reflectometry, and it'll show how far away the reflection is, and tell you how long, electrically long the cable actually is. And if you've got a discontinuity in it, like a kink or something that will cause a reflection, you'll see where that is and actually tell you how far from this end it is. A bad connector would show up. Lots of things like that you can do. This is a typical, one of the popular ones by MFJ over here on the left. I think that's a 259. Been around for a long time. It's one of their better products. But it basically measures SWR. Does it over all these different frequency ranges. And the older ones have these meter displays. Some of the newer ones have more of an LCD panel, like this one has a small one here. Over on the right is a vector network analyzer. These have been popular in the last, I don't know, 5-6 years, I guess. These used to be very expensive laboratory equipment. Hewlett Packard and people like Roden Schwartz made them, thousands of dollars. In fact, there's still some that are, what is it, Greek? The Ukrainian made one. It's, I think it's Rig Expert is the name of it. And they're $300, $400, $500. These, I guess they're made in China, over here in Asia somewhere. They came up with it. You can get them for about $80, $90. They will do essentially everything that the expensive ones will do. They may not have the frequency range. These typically only go up to maybe 3 gigahertz. They handle about 10 milliwatts of power. That's about what they put out in the transmit mode. Because you can use both ports, so you can send the signal out through one port, receive it in the other, and see how much loss there was. That's how you check a coax cable for loss. And they usually come with some accessories like calibration tools. You'll have an open, a short, a 50 ohm load, and a feed through, so you can calibrate it for the frequency range and some adapters. There's some PC applications. You can connect it through USB to your computer and get the display on a much bigger screen and be able to print it out and do things. They're much more versatile, and these are in the couple $100 range, so it'll do more things than this. This is sometimes a little harder to read, particularly outside because of the display, but they're well worth the money. Okay, which of the following is used to determine if an antenna is resonant at the desired operating frequency?
Bravo.
If an antenna's impedance is not 50 ohms, the transmitter end will not appear to be 50 ohms because of the way coaxial cable works, or a transmission line works. It has to be terminated on both ends in its characteristic impedance, or the characteristic impedance changes. So not only do you have the reflection problem if you've got a mismatch, your coax isn't exactly 50 ohms anymore either. It becomes more frequency dependent. When it's terminated, it doesn't change impedance over, in theory, the whole frequency range, which is one of the important things why you can use it. You can use what everybody calls antenna tuners or couplers to transform the impedance back to close to 50 ohms. And basically all you're doing is trying to cancel out any reactive components that you're seeing on the transmission line in the antenna. Because the whole thing is to eliminate any reactive components, so all you have is resistance in your impedance.
So can you just slap a choke on it or something?
No, but the choke will get rid of common mode that you can see on the shield. We don't go into that on the technician, but if you have imbalances on your antenna, on the dipole, for instance, most of them are variations of dipoles. Because the way the coax works with the electric field, the current going up the center conductor or down, depending on the polarity at the time, is going to be equal and opposite of what's on the inside of the shield. Okay. However, because of the skin effect, any imbalance on the antenna, which means I've got an amp going up, I should have an amp coming down, but I got an amp and a half. Where's the half amp go? It comes down the outside of the shield. It actually looks like two conductors, an inside and an outside. And that will go all the way back to your station, okay, as common mode current. And it can get in and, depending on how big it is, can cause problems. It's radiating because it's a wire with current flowing on it. So you use a common mode choke or a current balun to provide an impedance. So what you're going to do is put usually ferrite beads, or you run the coax through a number of turns in a ferrite toroid, So you're making it an inductor. So impedance goes up with frequency, so you can block those frequencies. So you got to get it. You normally want it to be at least several hundred ohms down at the lowest frequency you're using. And of course, the impedance will go up the higher the frequency. So it will block that common mode current. But we don't do that in technician. Okay, so the bottom line is it's impedance matching, not antenna tuning. What's the major function of an antenna tuner or antenna coupler?
Alpha.
Okay, one of the other tools is a dummy load. If you're testing or you're just trying to tune things up, then you don't necessarily want to transmit, because according to FCC rules, when you transmit, you have to give your call sign. Which, if you're just testing stuff, if you connect your system up to a dummy load, which is a 50 ohm resistor, usually on a heat sink, so there's no inductance or capacitance in theory. It looks like a pure 50 ohm resistance. Then you can test your system without actually transmitting. So you can run, like in that case, it's just 300 watts. If you look on the back of it, there's probably a chart, and it shows you how long you can do 300 watts, which is probably just a few minutes.
Mm-hmm.
But it would probably handle 100 watts for quite a while, or 50 indefinitely. But it essentially prevents you from transmitting over the air when you're dinking around with your system and trying to make sure. I mean, one thing you want to see is if you can put 100 watts out into a 50 ohm load before you hook it up to the antenna. But then you got a whole different issue, but at least you know that if it was a 50 ohm load, your system's working. So what's the primary purpose of a dummy load?
A.
All right. What is a dummy load?
B.
If you notice D down there, it says a 50 ohm reactance. You don't want, that's the whole point. It's resistive, there's no reactance to it. Okay. Well, we really whipped through them today. 1 block.